Hi. We don't have many people here, so I think you can speak freely. Let's look at example 9. So let f of x be a continuous function, and then please show that this integral is equal to another integral. And then you're going to evaluate something. This one, the first question, to prove that the two integrals are equal. Now, eventually, you should understand that the left-hand side is a value and the right-hand side is a value. So they're equal that way. Now, to prove it, there are some things you can follow. So it's quite obvious. I mean, maybe through the product, if I show you the answer right now, you will say, or maybe you will say there is really no reason why you can see that this is the way to go, because it's just a method of substitution. Now, first of all, the left-hand side, really there's nothing to change. It's the most simplified form of writing this integral. However, if I change this to another variable u, like let's say let x be a minus u, and we do that simply because on the right hand side you can see the same a minus x, so I'll let x equal a minus u, and therefore even though it's not obvious now, but later on you will see it's obvious. So if you see that one moment. Okay. Let x be a minus u, then dx equal negative du. And then we can also figure out the limits when x equals 0. Then u equal, now I guess we have to know that u equal a minus x as well. So it's easier when you have this equation. So when x equals 0, u will equal a. And then when x equal a, u will equal 0. So that the left-hand side integral, right now, if I change the variable, it's equal to everything being changed. That's 0 changed to a. The upper limit a is changed to 0. And f of x is changed to f of a minus u. And dx is changed to negative du, like that. That is the method of substitution. And afterwards, you don't have to change it back again. Remember, you only do the change of variable once. And then all you do is to simplify. To this simplify, I would take the negative sign in front. That's the first negative sign is put in front. The second is that we'll swap the lower limit and the upper limit. So the negative sign disappears. Okay. And then my last step is to change the variable back to x, so that it looks exactly like the right-hand side. Now remember the last one. This one is to just change the variable and not affecting the integral's value. I'm not saying that u and x are equal. I'm saying that if I change the variable u to x, the integral does not change value. Is that fine? So this is not a substitution per se. So the first one is the substitution. And the rest are all simplification. Is that okay? To understand that the left-hand side and the right-hand side are equal. So let's go back to this equation. This equation reveals us that even if f of x and f of a minus x are two different functions, however, if we integrate, that is to find the area under the curve, the two different curves, even though they are different curves, but the area under the curves are equal between 0 and a. I know it's hard to believe, but really, they are equal in some way. Now, this is a sort of an identity, an equation I found. Perhaps I can use it to solve this integral part B. So from here, 0 to pi over 2 sine x divided by sine x plus cosine x dx. Now, first of all, you may need to write it down, but you need to realize that I need to assign a in this part. A can be anything, so I will assign a pi over 2. And also f of x can be just this function inside. So that this required integral is exactly, this required integral is the left-hand side of the equation. And then it's equal to the right-hand side of the equation. And I will not change the lower limit and the upper limit. I will not do the change of subject and do part A over again. In fact, I'm going to use the right-hand side of the equation directly. That means to change the function only. So the lower limit and the upper limit, they stay the same. And then I will change the function to f of a minus x. That is to replace x with a minus x. So here I'll write down a minus x. Okay. And then after simplification, you will get that this integral and this integral are equal. Okay, now remember that I am not saying this function and this function are equal. They are not the same function, but I'm saying that this integral is equal to another integral. And that is very important to know before you can set out to find the value of the integral. Because the next step, I'm going to add this one to this one. Now, since this one and this one are equal, so I'm saying that one of them, the left-hand side, must equal the left-hand side plus the right-hand side divided by 2. You see, that's it's a new technique. If you prove this integral and this integral are equal, then you can say one of them is equal to the sum divided by 2. That's why I'm adding this to this and divided by 2. And it's very good when I do that, because this integral add this integral, and then I can add the function to the other function, and I find out the outcome, the function outcome is 1. So even though this function and this function, either of them are easy, I can still find the sum of their integral pretty easily. So this is equal x, and that is y. The final answer is pi over 4. Now, this example is an extraordinary example when an identity is proven. Now, when I call this identity, this is because this equation can be used to simply every continuous function, you know? So f can be anything, not just this function, to any other functions as well. And also can be used when a equals to anything as well. So that's an identity. And when this identity is proven, this one, although I don't know if you can sense that, but I think to find the primitive of this function is pretty hard. It's not easy. To find any primitive function is not easy. That is, to find the indefinite integral is not easy. It's not easy, especially for this one. I do not know the correct technique to do that. However, when I find this identity and I apply this identity to this function and create this equation, I can find the integral. So that's a brilliant way of doing so. Let's move on. Example 9. I think it's example 9b. Prove another identity. Again, this integral equal to another integral. Okay. Now in this case, I will let x be 2 minus u, then du equal negative du, dx equal negative du. And also I should have written this down. That is u also equal to minus x. So it's easier when I do this. When x equals 0, u equal 2. When x equal 2, u equals 0. Okay. Now this left-hand side of this integral, when I do the substitution, I need to change everything. Change everything. That is 0 to 2, 2 to 0. F of x is changed to f of 2 minus u. D of dx is equal to negative du, and that is my substitution. Afterwards, I only have simplification to do. That is to take out the negative sign. Again, to swap the lower limit and the upper limit. And my final step, that is to change the variable back to x. Now, only the first step is considered as change of variable, substitution. The second is simplification, the third one is simplification, and especially the last one. Especially the last one. Now I'm going to repeat this. It's not that I think x and u are equal. I'm just indicating that if I change the variable from u to x, integral will stay the same. There is no way I would say x and u are equal, okay? Because at the beginning, I already assigned x equal to minus u. this one does not imply x equal to u. And then after this integral, after the identity is proven, perhaps we can figure out how to find this integral. This integral is hard. It's hard. So in this question, we have to assign that in order to use the identity, we have to know what f of x is. You don't have to write it down, but I think in your mind, you should remember f of x in this case must equal to 1 divided by 1 plus e to the power x minus 1. Okay, and then afterwards, let's use this identity. Oh, sorry, did I say this is x? Oh. Why do I write u again? Now afterwards, you would change this integral to another integral, but do not change the lower limit and the upper limit. You only change the function. So the function is changed. Instead of writing 1 divided by 1 plus e to the power x minus 1, I'm going to change x to 2 minus x. So here, the only change here is 2 minus x. You see? Now pay attention, the only thing I change here is x is changed to 2 minus x, nothing is changed. And look here, this identity is that nothing is changed except f of x is changed to f of 2 minus x. Now this one is not considered as a substitution. This one is considered as the application of the result of A. Moving on. Now we only need to simplify. To simplify, of course, this is 1 divided by 1 plus e to the power 1 minus x, right? That is to simplify. And then another simplification. I guess you can do it anyway, but I will do it by multiplying e to the power x minus 1. This is also to simplify. Now this is because I want to make sure that this denominator is changed back to the same denominator. Now when I do that, I will get another one that is e to the power x1, x minus 1, divided by e to the power x minus 1. And this one, e to the power x minus 1 times e to the power 1 minus x, that is equal to e to the power 0. Which is 1 in the end. So this technique will help me quickly get the answer because I want the denominator stay the same as the original function. Okay. Now I use the same technique. Now, even though the required integral is difficult to find, I can find the sum. I can find sum. So the left and the right, they are equal. That's why the left is twice of the left is equal to the left plus the right. And the left plus the right is easy function. The function is easy. So that, and that is this. 0, 2, 1. Is that okay? Do you have any question? If no, we move on. We'll move on. You can stop me anytime because only 2 of you. Classwork. Let f of x be a continuous function You show that f of x integral is equal to f of x to f of 2 minus x integral. To do that, you need another variable. Let u equal 2 minus x. I guess it doesn't hurt to write x equal 2 minus u as well. Then x equal 2 minus u. And then you will write dx equal negative du, right? And also it's a, right? Sorry about that. We need to change the questions to a. Otherwise, it won't work. It's a. It's a. So this one is a. I thought so. It's u equal a minus x. X equal a minus u. Otherwise, how can it be 2? It's a. And then dx equal du. And then the limits, when x equals 0, then u equal a minus 0 equal a. When x equal a, u equal a minus a equals 0. And then we're ready to do the change. That is from 0 to a, f of x dx, change to, the first is very important. You have to do everything all at once. Very important. That is from a to 0, f of u, a minus u, negative du. Very important. Very, very important. Have to do this everything at once. If you only change the function and then you don't change the limits, it's wrong. Okay, it's wrong. It's not considered as correct. And then to simplify, to simplify again. And still the last simplification is the hardest. That is to change u to x. Have you learned? The first step is a substitution. The rest is just simplification. Especially the last step. The last step is just, yes, the last step is just to change u back to the variable x. And then the identity is proven. Part B. In part B, to evaluate this, You may not have to write it down, but you must know that in this case, a must equal 4 and f of x must equal to this one. So to use the identity found in part A, you would just claim that from 0 to 4, f of x dx is equal to, nothing is changed, still from 0 to 4, another function. And this function, you should write another function, which is f of 4 minus x. So nothing else has changed. Dx is not changed. But here you should write f of 4 minus x. So every time when you see x, that's 4 minus x. This one also 4 minus x. And the second one is 4 minus bracket 4 minus x. Maybe I remove it. That is the change. Remember here, in this identity, the left-hand side from 0 to a, the right-hand side from 0 to a, the only thing changed is the function. And that's what I did. I changed the function to another function. And to simplify the function, it's easy to simplify. Do not expand. Do not expand. Do not expand, just simplify. Okay. Now, right now, you would say that on the left-hand side and the right-hand side, the two integrals, they are equal, and they're both difficult to find. However, their sum is easy to be found. So I will add, so one side is equal to both sides divided by 2. So 1 over 2, both sides one side is both sides divided by 2, and then both sides, the sum is easy. And then it can be found. And that's it. Do you have any problem? I think not. I think not. There are a lot of exam questions designed this way. I hate to say it, but it's true. A lot of questions designed this way is that although the target integral is difficult to be found, but using an identity or something like that, it can be solved. It can be solved. Now, if you master this technique, then it's fine. But what if, I don't know, I don't know. You just need to practice a lot. But I will also take this opportunity to explain to you why this could happen. This could happen not because this method is so good or anything, is because there is some like profound reason behind it. Let's take a look at this function f of x and its graph. Should I? Maybe not this one. You see that the three questions we just explained are very similar. So I will take this one because this one has 2, right? I'll take this one, 9b, as an example. And I will show you why, what is the profound reason behind it, especially this identity, why the existence of this identity, how can it be recognized, and why do we know that we need to use this identity? So to our graph. Now on this graph, I will show you what's f of x, and here I will use this one, f of x. 1 divided by 1 plus e to the power x minus 1. That's f of x. It doesn't look cool, but you can see. Is it fine? That's the function. Is there anything extraordinary about this function? I don't see anything so special about it. It's just a curve that we use anyway. However, if I do this, I can do the integral. The integral can be f and value a from 0 to a to 2. Also, it shows you what the answer is, but still, let's say we don't know what the answer is. That's the integral. Let's say that's what the integral is. Okay. From 0 to 2, the integral of f. From 0 to 2, from 0 to 2. Now, obviously, the calculator can give you exactly the answer very quickly. But let's say we don't know what the answer is. However, now what is the profound meaning behind this identity is that we can try to plot f of 2 minus x. So here I will have g of x. So I will type g of x equal f of 2 minus x. You see, I just type in g of x equal f of 2 minus x. Do you see the definition of g is f of 2 minus x? Now, although we don't see anything extraordinary about f itself, but right now I hope that you can see there is a very clear relation between f and g, that is f and f of 2 minus x. You can see that these two are symmetrical along something, and that is x equal 1. These two are symmetrical along this line. And that's not very difficult to understand because essentially g of x is a reflection of f of x and a translation of that result. Now let's go back to let me go back to the notes. Now, you can see that when f of x can be reflected to f of negative x and also translated to the right. I think so. Translate to the right. Yes. Reflected and translated. right? This one is reflected and translated to get f of 2 minus x. So reflected and translated. So I can also show you the reflected one. So this one, the green one, can be reflected h of x equal f of negative x, this one. So it can be the green one is reflected and then translated to the red one. You see? That's reflected and translated. Now the green one is reflected to be the blue one, and then the blue one is translated to the red one, so that the final result, if we ignore the middle, this is the middle, h of x is the middle. If we ignore the middle, then the final result, the relation between the green one and the red one, is that their relation is that they're symmetrical along this line in the middle, x equal 1. Okay, so this integral that you see, this integral from 0 to 2, from 0 to 2. And then I will show you another integral from 0 to 2. Now, if you look at my typing of this integral, that is to integrate g between 0 and 2, then you get b, right? You can see that a and b, are they different area? I think they are they look different, but they are of the same shape, exactly the same shape. It's just a is this way. A is this way. That's a. And b is this way. It's b. That's b. And that's a. Is that clear? What I'm trying to say is that this identity in this previous half an hour, we proved this 3 times, but in reality, why they are equal is that there is some symmetry between f and f of 2 minus x, some kind of symmetry. There is a symmetry. Some kind of symmetry. Okay, between these two functions. Therefore, although these two functions are not exactly the same, however, from 0 to 2, the integral, their integrals from 0 to 2 are equal in value. Is that okay? I hope that's fine. I hope that's fine. And that will explain to you how this works. In fact, if I go back to my this plotting, I can actually change f to anything. I can change f to perhaps the classwork, that is x to the power 3 divided by x to the power 3 plus 4 minus x to the power 3. Like that. I can change it to that. Okay. Did I type something wrong? It's x to the power 3 divided by x to the power 3 plus 4 minus x to the power 3. Right. And then they're all changed. And anyway, this integral is not from 0 to 2, it's from 0 to 4. I changed it to 4. And this one will be changed to from 0 to 4 as well. Is that okay? Yeah. G 0 to 4. F 0 to 4. Why is it not the same? F 0 to 4. G 0 to 4. Oh, sorry, I made it wrong. G is not 2 minus x, G is 4 minus x. Oh, sorry. Yes. You can still see the symmetry, even if I change to the setting of the classwork. Let me see the setting of the classwork. The setting of the classwork is from 0 to A, and A in this case is 4. You can still see that there is symmetry between f of x and f of 4 minus x. There is symmetry. There is symmetry. They are symmetrical along x equal to. They are symmetrical along x equal to. And because of the symmetry, the integrals are equal. You see A is from 0 to 4. That's A, and that's A. This is A. From 0 to 4. This one is difficult to be found. 0 to 4. And this one, B, from 0 to 4. They're not the same integral, but the outcome is the same. In the future, if you are asked to prove any other kind of equation, and if they are true, they're true equations, that means, it often means that there is something symmetrical about it behind the scene, because when you prove it, you don't really plot the graph, so you don't see what you're doing, but behind it, the reason that there are these identities around is because of the symmetry. Is it fine? I can move on. I can really move on. But is it fine? Is there any question you want to ask me? Since we only have you two. Gladys, can you handle this?
Yes, thank you.
How about Emily?
Yeah.
Is it fine? Because if I move on, there will be something else added. But right now, it's just these 3 questions. If they are changed to some other functions, you should use exactly the same method to find out the integral. Is it fine? Because my next example is not the same anymore. Make sure you can handle it, okay?
Yeah, it's fine.
Okay. Now the next one, in fact, I haven't sent you. So I will send you right now. It's in the Google Classroom. There are 2, I think. In the Google Classroom. Definite integral. Where is definite integral? There. And I need to add another file. That is this file. And this is the new file added. There are 2 questions inside. Now you should go and download, or you can screenshot, because I'm going to show you right away. Hmm? One moment. Oh, that's okay. Now there are two questions in the file. I call them example 9C and example 9D. Now, I really hope you're fine with the previous three questions because this one is going to be new. It's a little bit new. It's not a lot, but a little bit. And you can see that there's still part A is an identity to prove, and part B you're supposed to use it. Okay. And how do we prove this? No, how do we even prove it? I don't know. You can try a little bit because I need to try as well. I will try first and then I'll get back to you. Is it fine? I'll pause this recording. Okay. Now you now need to pay attention because the answer is coming. The answer is coming. And this identity obviously is more difficult, right? So what I'm going to do, this is after trial and error. It's not like I can figure out exactly what to do in the first try. I can't. But after trial and error, I decide that this is the substitution I'm going to use. It's almost the same substitution. This is the substitution I'm going to use. And also x equal a minus u, right? Therefore, dx equal negative du. And when x equals 0, u equal a minus 0 equal a. And when x equal a, u equal a minus a equal 0. Up to now, this is just in preparation of the substitution. Now, to get to the real part, after I decide this is the substitution I'm going to use, I will only use it on one part of this equation. Means that I will use it on only one part, one particular part of this equation, that is this part. Okay, so the left-hand side, it has this part, which is from 0 to a, x times f of a minus x dx. This is the only part I'm going to use this substitution. Now, later on, you can think back at the aftermath of it and why do I only use it? I can explain later. But first of all, I'll just use the substitution on this part, which is x times f of a minus x dx. And in this part, I will change it to a0 u minus a f of a minus x, that's u, and then dx change to negative du. At this part, you must do it perfectly because the substitution, it has to be all correct. You figure out x is changed to u minus a minus x is changed to u, dx is changed to negative du, and also the lower limit is changed to a and the upper limit is changed to 0. So there are 5 things changed. 5 things. Now I will simplify by taking out the negative sign. And also to flip the limits. And the last thing is to change u to x. Okay. And again, the last time when I change u to x, I'm not saying u equal x. I'm saying the integral equal to the integral. Is that okay? Now, to use the equation, the left-hand side, I think I can write it here because the left-hand side from 0 to a x f of x plus, plus f of a minus x dx can be changed to 0 to a x f of x dx plus from 0 to a x a minus x dx, right? And then I'm not going to change anything here, but I'm going to change this to this. Now, please pay attention. This is changed here. So only that part is changed. And now when I put them together, a x f of x plus x minus a f of x dx and then it's equal to 0 a x f of x plus did I make a mistake? A minus u, a minus u. Let me erase this. Now let me use another color so it's clear. This one I made a mistake. It's a minus u, a minus u. Oh my god, a minus u. A minus u. X is a minus u, yes, a minus u. So this is a minus x. Sorry, I made a mistake. So this is a minus x. A minus x. Okay. Okay. So this one is a f of x minus x f of x close bracket dx, and that is from 0 to a f x dx, and that is a 0 a f of x dx. Made a mistake. Is it fine? Now the aftermath. The reason we only apply the change of subject, substitution, change of variable in this only this part is because, of course, my first trial didn't work. There was some, because I failed the first trial. If I use it onto everything, then in the end it doesn't work out. And also because I noticed that the x times f of x must remain at this part, because the right hand side also has f of x, right? That is a sign that I need to keep it. So this one is not changed. This one is not changed. So only this part is changed, and this identity. Right now it's this. Right now it's this. So if you ask me what is the geometrical meaning behind it, I would still say it's the same symmetry, because I only replaced this one, and it's the same symmetry. Okay, and then the sum, because the first part is not, it's just that when you add this part or this part, they cancel each other out, and then you have a times x, and then a can be taken out, basically. Is it fine? I'm sorry, I made a mistake. I don't know what I was doing. The a minus, it's x equal a minus u, not u minus a. It's a minus u. I wrote it there. I just copied it wrong. Also, in the end, it doesn't work out, so I'll have to go back and check. So that's it. The equation is proven. The equation is proven. Okay. Now, right now, how to use the equation, you need to find some resemblance between this required integral and the left-hand side of this equation. You need to line up which one is a, which one is f of x, and which one is f of a minus x. Now, so to do that, I must first realize that in this case, a must be 1, because that's the upper limit. A must be 1. The f of x must be 1 over x plus 3 to the power 3. Like that. Okay. As to the f of a minus x, it must be the second one, but we cannot be too arrogant to think that it must be. So we need to calculate. So how about f of a minus x? In that case, it's 1 minus x plus 3 to the power 3. And that is 1 over 4 minus x cubed. So that will make sure that everything lined up. Let me underline. So f of x, this is f of x. This is f of 1 minus x. That is this, and then I line up with the left-hand side of this inequality of this equation. Now let me use it. Now we know that from 0 to 1, x times f of x plus 1 over close bracket dx. Obviously, this is too difficult to figure out. However, in the right-hand side, it doesn't have x and anything else. They only have a is outside, 1 is outside, and then from 0 to 1, f of x only. So 1 over x plus 3 to the power 3 dx only. So that integral is simplified to a much, much, much simpler integral. Okay, obviously not as simple as the previous examples, because after simplification, the integrand inside is 1, but now this one, still you have to do something, but it's not as difficult as the original. Look at the original. This is the original. But now it's the simplified one. And this one is much easier because we can find the indefinite integral very quickly. So this one is from 0 to 1, x plus 3 to the power negative 3 dx plus 3. And that is equal to 1 divided by negative 2 x plus 3 to the power negative 2, and this value from 0 to 1. In that case, 1 over negative 2, 1 minus 0. Okay. And this is not easy. I just want to make sure it's correct. 1 over 2, 4 to the power negative 2. And then this is plus 1 over 2, 1 over 9, right? So in the end, it's 1 over 2, 1 over 9 minus 1 over 16. So that is equal to right? So anyway, that's the answer. Tell me if you have any question. I'll pause for 3 minutes. Okay. Last question of today. Now this question, I changed the question a little bit because I don't want the lesson to be too repetitive so that the identity is given instead of, oh, you're going to prove it. Is given. Now you only have to think about how to use it. But it's fine that if you want to, later on after the lesson, if you want to prove this identity, that's fine. That's fine. But right now, let's just assume that it's already proven. Okay. Can we use this identity to solve our integral? Now this integral is extremely difficult. I don't see any reason why we can't. There's no way we can find the indefinite integral. So to use the identity, to use the symmetry is the only way out. Okay. Now to use that identity, we must make sure that we know what is f. Now here it's clear that f is that. So let f be x times sine x divided by 3 plus cosine x. Right? Now, in order to use that identity, I better figure out f of pi minus x before I use it. So I want to do the simplification before I use it. So I want to find out this. So I want to simplify before I use. Okay. And the simplification is not extremely difficult because this bracket I will not expand. I will not. And then sine pi minus x and sine x are equal. 3. This one is negative cosine x, but however it's squared. So in the end, you'll find it still the same denominator. Okay. Now let's apply. Now we know that this integral and this integral are equal. Okay. Now you can always do that. You can do the simplification first and then use the identity. Is that okay? Now, let me say it again. Now, I never said these two equations, these two functions are the same. This function and this function, they are different functions, okay? This function and this function, they are different functions. I never say they're equal. I just say that the integral is equal. Okay? Now, to find the integral, you will have the left-hand side equal to 1/2 the left plus the right. Plus the right. So one side is 1/2 both sides. And then after addition, Still not ideal. Still not ideal. But I can have most of the things I don't want eliminated. So the x sine x, that's pi sine x minus x sine x. So that's pi sine x 3 plus cosine square x dx. Now in the previous example, the easier ones, when you add them together, it's a very simple one, the result. But this one, after adding, it's simplified, but not simply enough, just not simple enough. So this one is much simpler because I can take out pi, but I still have sine x and cosine x inside. Okay, now to figure out this one, you can't use the identity again. You simply can't. So here I'm going to use all my techniques.
Miss Chen, Miss
Yeah.
Chen. May I know whether like the 3 should be pi instead?
Oh yes, pi.
Thank you.
I don't know why I wrote 3. Yeah, it's pi. Pi. It's pi. 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 Yeah, sometimes I don't know. There. Now, right now, it's just the integration time. This one is the indefinite integration. So my first technique is to use this. That is d negative cosine 3 plus cosine squared. Now here I'm using sine x dx equal d negative cosine x. Now, that's a substitution. And because I didn't change the variable, so still the lower limit and the upper limit is not changed. Okay. And then after this, I will simplify a little bit. Negative pi over 2, 0 pi. D, it's 1 over 3 plus this d cosine x. So there is a little bit of simplification when I take out the negative sign. Is that okay? It doesn't look great though, but that's what it is. No. If you want it to look better, maybe there is a change that you can do. No. If you want it to look better, you can say that, oh, let cosine x be t. No, let me write it here. So if you want it to look better, you can let t be cosine x. And when x equals 0, t equal cosine 0, that's 1. And when x equal pi, t equal cosine pi, that's -1. Now, if you change it to this, I think it's easier this way if you want it to look better. In fact, I do think this looks better. Right. Now, if you want to use another variable, then you have to change the lower limit and the upper limit, I guess. And for this one, you can simplify a little bit because the negative sign, you need to swap the lower limit and the upper limit anyway. Is that fine? So that is my first change of variable. It's a lot simpler, huh? If you say, oh, this is y, where is the end? But it's much simpler though. Do you see at the beginning what it looks like? Now, if you look here, the original, and now it is a lot simpler now. It is, huh? But still, it's not solved yet. And to solve it, you need to use more technique. At this part, I will use t, change it to another variable. So in fact, yes, this is extremely difficult because after changing x to t, I'm going to change t to theta. And this time, I need to use another variable that will let t equal √3 tangent theta. Now we know that dt will equal √3 secant square theta d theta. And when t equal -1, -1 equal √3 tangent theta, and tangent theta equal -1 over √3. That means theta equal -π/6. Okay. And also this is hasn't ended yet. Now when x equal 1, when t equal 1, you can say 1 equal √3 tangent theta. So that means tangent theta equal 1 over √3. So theta equal 30 degrees. So this is my next one. So this change of variable π/2 from -1, that's -30 degrees. To +30 degrees. And then this is 1 divided by 3 plus t, that's √3 tangent theta whole squared. And dt is changed to √3. Maybe I write it here. That's √3 secant square theta d theta. And this will equal π/2 from -30 degrees to +30 degrees. This one is √3 secant theta square d theta divided by 3, 1 plus tangent square theta. And finally, this one is okay. And that is π/2 from -π/6 to π/6, √3 divided by 3 d theta. So in the end, it's π/2 √3/3 theta from -π/6 to π/6. This value is π/2 √3/3 π/6 minus √3/3 -π/6. So in the end, what is it? √3/18 pi squared is the answer. Is that okay? I know, I know. because the first part is given, the identity is given. So I think the focus is shifted to the calculation. Now, of course, the application of this identity is still important. This is the application of this identity. I think up till here, still doing that. So I think half is doing the application of this identity. However, because of the nature of this question, after you use these identities, still, it's a quite difficult integral. You need to do the substitution twice to find the final result. I'll give you some time. I'll give you 4 minutes. Okay.